Every crop we plant, every agricultural landscape we manage, impacts greenhouse gas emissions. Understanding them is not an option, it's a necessity.
As we are reducing our greenhouse gas emissions from other sources like transport and energy and households, the relative proportion of agriculture and land use is gradually increasing, so we cannot really reach the net zero target without reducing our emissions in that sector. Land use is a very complex topic. Land use is in part related to people's culture, people's values, local communities and livelihoods depend on it. And agriculture is a very important economic sector. It employs a lot of people in the UK.
The UK peatlands are significant landscapes for land management. In particular, the rich and productive soils of the fenlands of East Anglia, which support a variety of crops and sources of animal foods.
Peatland in its natural state is wet, and it actually takes up carbon from the atmosphere, so it helps reduce the greenhouse gas emissions that we emit from fossil fuel burning and oil and gas and so on.
But its use in historic management also means it's a significant contributing factor in agricultural greenhouse gas emissions.
But as soon as we drain the peatland, it starts emitting carbon dioxide to the atmosphere.
Reaching a balance between the reduction of harmful greenhouse gas emissions while maintaining food security and rural economies is critical.
So it's intensely complex because you have dealing with humans and the way they relate with the farm practices in the landscape and the history that is behind that. There needs to be a balance between the interest of high productivity out of farming with other interests such as ensuring that there's biodiversity and conservation also occurring across the landscape to enable policymakers make those decisions at a localized level but also at a national level, basically shape the outcomes of what is feasible as a policy instrument, as a policy tool.
Data-driven agriculture is the key to achieving this sustainable future. Currently, even simple modelling can take several days to generate results and is driven by past climate conditions. In situ measurements of environmental conditions are limited in number and geographical locations. AI for Net Zero is the power of deep machine learning, providing insights from the ground up. Science, research, industry and technology working in collaboration.
So I'm an environmental data scientist on this project. I create pipelines through which all the geospatial data is ingested into the machine learning and AI algorithms that we use. What we are interested in is what's called optical satellite data, which uses the visible and the infrared bands in the electromagnetic spectrum, and that kind of information is able to tell us about vegetation growth, moisture parameters, and essentially helps us see how these environmental elements are related to CO2 emissions from the peatlands. So when you do download this data, it's essentially just data. To convert it into information, we need to be able to get useful insights out of it. So that's where the AI and the machine learning models come in.
Blending mathematical models and diverse data sources, this physics-informed graph neural network acts as a prediction engine in a self-learning digital twin.
This is one of the first projects that are trying to bring in physics-informed machine learning into the self-learning digital twin capability to build a digital twin that does not exist before.
This project really is at the forefront of developments of the digital twin technology. We are experimenting with self-learning digital twins, where the machine learning models are self-improving over time based on new data that they are being fed, and they are constantly improving their knowledge of the system as it evolves over time.
Trying to self-learn almost in real time and dealing with all the computational complexity of the underlying models has been extremely challenging. At one level, we are trying to create a data from the simulation models. Number two, we are trying to embed that mathematical functionality into the learning function so that our learning is still mathematically and empirically verified. And number three, that we can do it in a fraction of a second so that we do not have to wait ages or days and months. We could do it in milliseconds and probably in few seconds at the most, actually, even for complex decision scenarios.
Giving farmers, communities and policymakers the data and vision to make real change right where they are, at speed, at their fingertips. Users virtually plant a variety of crops, choosing what to grow, where, how much, and the levels of resource management, such as irrigation. Incorporating external data sources, the digital twin delivers rich visualizations, overlaying additional geospatial information, allowing users to build detailed insights and predicted outputs of greenhouse emissions and crop yields.
And I see this project as being part of a bigger picture of being able to create an instrument that can be rolled out potentially globally, based on the possibility of actually giving policymakers tools that they can use to make decisions that closely resemble, closely relate, and understand the ground realities.
Because we have taken into consideration opinions and concerns of people from different domains, I think it makes it more realistic as a solution.
Giving farmers, communities, researchers, and policymakers the data and vision to interrogate, influence, innovate, and develop sustainable farming practices and peatland restoration approaches. AI for Net Zero, the power of AI and digital twinning, moving us towards a sustainable future that drives down emissions and secures food security.